Stars, like living beings, have life cycles. They are born, they shine, and eventually they die. But what determines how big a star can grow before it reaches its limit, or what happens when it can no longer maintain its structure? To explore these questions, we need to take a closer look at the nature of the largest stars known: supergiants and hypergiants, some of the universe's most massive and luminous objects. Supergiants are stars that have expanded to an enormous size compared to our Sun. While our Sun's diameter is about 1.4 million kilometers, some supergiants can swell to hundreds or even over 1,000 times that size. Imagine a sphere so large that if placed in our solar system, it would engulf the orbits of Earth, Mars, or even Jupiter. These stars begin their lives as massive, hot stars called O or B-type stars, which fuse hydrogen into helium at rapid rates due to their high masses, often tens to over 100 times the mass of the Sun. This intense fusion generates enormous outward pressure that counteracts the star's gravity, preventing it from collapsing inward. However, as these massive stars use up their hydrogen fuel, their internal balance changes. The fusion begins to take place in shells around the core, causing the star to expand dramatically. At this stage, the star becomes a supergiant. Its outer layers balloon outward, its surface cools slightly, and its appearance changes. The famous star Betelgeuse, a red supergiant located in the constellation Orion, is an example of such a star. It is about 700 times the Sun's diameter, large enough that if it replaced the Sun, its outer surface would extend past the orbit of Mars. Going beyond supergiants, we encounter hypergiants, an even rarer and more extreme class of stars. Hypergiants are some of the physically largest and most luminous stars observed, typically exceeding 100 solar masses. They not only shine with incredible brightness, but also undergo intense instability. The internal pressure and intense radiation from these stars become a delicate balancing act. The outer layers of hypergiants experience massive stellar winds, blowing material off into space at prodigious rates. For example, the hypergiant star Eta Carinae is famous for its violent outbursts and the large nebula it created, visible through telescopes as the Homunculus Nebula. The sheer size and mass of these stars make them extreme examples to study, but even these giants have upper limits. Observations and theoretical models suggest that stars cannot grow endlessly. Several factors where such limitations arise are driven by fundamental physics. First, the famous Eddington limit defines the maximum luminosity a star can have before radiation pressure pushes its outer layers away faster than gravity can hold them back. In simpler terms, as a star grows larger and brighter, the pressure from the intense light it emits can start to blow off its material. This radiation pressure counteracts gravitational pull, and when it gets too strong, it can limit the star's mass and size by driving strong stellar winds that peel away the outer layers over time. This means that beyond a certain mass, 150-200 times that of the Sun, stars become unstable and lose mass rapidly. Second, there's a practical limit related to how the star forms initially. The gas clouds from which stars are born have finite sizes and densities. As a cloud collapses under gravity to form a star, the growing radiation from the protostar pushes outward, sometimes disrupting the infall of more material. This feedback effect means that very massive stars are rare, in part because it's hard to gather enough gas into a single newborn star before the radiation halts further accumulation. Thirdly, internal stellar physics plays its role. Massive stars burn their fuel at extremely rapid rates, leading to short but turbulent lifespans. Their cores fuse heavier elements stepwise, moving from hydrogen to helium, carbon, oxygen, and so on, until they reach iron, which cannot sustain fusion. At this point, the delicate balance within the star's interior falters, and the gravitational forces can no longer be balanced by the outward thermal pressure. When this balance tips, the star ultimately collapses. What happens during this collapse depends largely on the star's mass. For giants and supergiants that have reached the iron stage, the core collapses in a matter of seconds, leading to a supernova explosion. This explosion blows off the star's outer layers, leaving behind either a neutron star or a black hole as a remnant. This violent and brilliant end ensures the star cannot increase indefinitely in size because gravity, at the end of life, will overwhelm any forces holding the star up. Interestingly, the process of collapse is deeply connected to the star's inability to maintain its size indefinitely. Inside the star, the pressure that combats gravity is not just thermal pressure from hot gas, but radiation pressure from photons emitted within. As a star grows more massive, radiation pressure becomes dominant. However, there is a ceiling beyond which radiation pressure causes turbulence and instability in the star's outer layers. This instability leads to massive stellar winds and sometimes to episodic eruptions. Even before the star reaches the end of its fuel supply, these eruptions can reduce the star's mass dramatically. This feedback loop: a star grows large, radiation pressure drives mass loss reduces size, the star stabilizes or shrinks, helps impose the physical upper limits on star size. To put this in perspective, the largest stars known, such as VY Canis Majoris or UY Scuti, have radii more than 1,000 times that of the Sun, yet their masses are only about 20⁻40 times the Sun's mass. Their enormous size is due to their highly inflated, cool outer layers, which are extremely tenuous. Their mass is constrained much more tightly because of the self-limiting effects of radiation pressure and mass loss. On the other side of the size spectrum, stars that are not massive enough to ignite fusion become brown dwarfs, objects sometimes called failed stars. This shows that the conditions for existing as a star sit within specific mass windows. Too small and fusion never ignites, too large and the star becomes unstable. The interplay between gravity, pressure, radiation, and mass loss defines the life and size of stars. Gravity tries to pull matter inward, making stars contract and grow denser. Opposing this is the outward push, the thermal and radiation pressure generated by nuclear fusion reactions at the star's core. As fuel is consumed and fusion changes, this balance shifts and the star's structure and size evolve. Additionally, the environment around stars can influence their size and life cycle. For example, stars in dense clusters might be affected by nearby stars through gravitational interactions or the inflow of material. Moreover, metallicity, the proportion of elements heavier than helium, affects how stars transfer radiation outwards and how their atmospheres behave. Lower metallicity stars tend to lose mass less efficiently, which can allow greater maximum masses under certain conditions, like in the early universe. The story of star size is also entwined with questions about how we measure stellar properties. Because these enormous stars have extended, diffuse outer envelopes, figuring out their accurate radius is challenging. Different wavelengths of observation reveal different layers, complicating direct comparison. Nonetheless, the consensus from multiple methodologies supports the conclusions about mass limits and instability. In summary, the size of a star is not just a measure of how much gas it has, but a balance of complex factors including mass, radiation pressure, fusion processes, and the mechanical limits imposed by physics. Supergiants and hypergiants represent the upper extremes of this balance, immense in size but fragile and volatile. They cannot grow without bound because both the internal physical processes and external feedback they generate ensure mass loss and ultimately a dramatic collapse. Studying these massive stars offers more than trivia about size. These cosmic giants are key players in cosmic evolution. Their births, lives, and deaths help shape galaxies by producing heavy elements, triggering star formation, and making neutron stars and black holes. Understanding their limits helps us understand the broader processes that govern the universe. Although the universe has no shortage of surprising phenomena, the limits on how big a star can grow are a testament to the underlying laws of physics. Gravity demands that stars maintain equilibrium, and that equilibrium ultimately sets the stage for the grand pageantry of stellar life. Growth, brilliance, and the inescapable pull towards gravitational collapse. Beyond the boundaries set by radiation pressure and the Eddington limit, there's another fascinating layer to the question of a star's maximum size: the influence of rotation. Stars, in addition to shining and pulsating, often spin, sometimes wildly fast. This rotation affects their structure and their capacity to hold onto mass. When a star spins quickly, the centrifugal force at its equator acts against gravity, effectively reducing the gravitational pull on the star's outer layers there. Imagine a figure skater spinning with arms outstretched. The faster they spin, the more they feel a force pushing outward. Similarly, in stars, rapid rotation can cause their shapes to become oblate, bulging at the equator. This bulging changes how close or far various parts of the star are from its center, which impacts the pressure and temperature distribution throughout the star. But rapid spin also introduces limits. If a star were to rotate too fast, the centrifugal force at the equator could exceed gravity's inward pull, causing the star to literally shed material into space. This critical rotation speed is called the breakup velocity. At or near this threshold, the star begins to lose mass not just through radiation-driven winds, but because its outer layers are flung off by the fast spin. This phenomenon is especially relevant for the most massive stars, because they tend to form with higher angular momentum, the rotational equivalent of energy. In some cases, the interplay between high mass and rapid spin forces stars into one of the most dramatic endings known: a gamma ray burst, an extremely energetic explosion thought to originate from very massive, fast-rotating stars collapsing to form black holes. Rotation also influences how stars mix their internal layers. Inside a rapidly spinning massive star, the deep interiors experience enhanced mixing of elements, bringing fresh hydrogen fuel into the core and distributing the products of fusion outward. This internal circulation can prolong the star's lifespan and alter its path of evolution, potentially affecting how large it can grow before reaching instability. While rotation adds complexity, it works hand in hand with other factors that impose size limits. For example, magnetic fields, generated within stars and often amplified by rotation, can channel and constrain the flow of mass loss. Strong magnetic fields may funnel stellar winds along certain directions or trap material close to the star, changing its effective size and the way it loses mass. Assimilating all these influences, gravity, radiation pressure, rotation, magnetic fields, metallicity, and environmental factors, astronomers still observe a conspicuous upper limit in stellar masses, clustering around 150 to 200 times that of the Sun. This isn't just a numerical curiosity. It reflects the fundamental balance of forces and feedback mechanisms governing star formation and evolution. Modern observations back this up. The most massive stars famously studied in young star clusters, such as those in the Large Magellanic Cloud, the Tarantula Nebula region, reveal no stars exceeding this upper mass range. Even in the universe's earliest epochs with low metallicity, where theoretical models once suggested that stars might burst far beyond those masses, recent evidence points to similar mass limits. An especially intriguing aspect of this research concerns the first generation of stars, known as population III stars. These ancient stars formed when the universe contained only hydrogen and helium, no heavier elements, metals. Earlier predictions posited that without metals to cool the gas clouds efficiently, these primordial stars could reach masses well beyond the modern-day maximum, potentially hundreds or even thousands of solar masses. Yet advances in computer modeling and indirect observations suggest that even population III stars likely faced mass limits, though perhaps larger ones than current stars. Their enormous mass would still be constrained by extremely strong radiation pressure and rotational effects. These giant stars, if they indeed existed, would have burned out quickly, possibly exploding as powerful supernovae or collapsing directly into black holes, potentially seeding the early universe with the heavy elements needed to form later generations of stars and planets. Returning to stars nearer to home, the story of size limits is closely connected to phenomena observed in astronomy's most luminous and unstable stars known as luminous blue variables, LBVs. These stars, often very massive and nearing the Eddington limit, undergo episodes of intense variability, shedding large amounts of mass in outbursts. Famous examples include the star P Cygni and Eta Carini, which experienced a giant eruption in the 19th century. LBVs help astronomers understand how stars approach their size and mass limits, because their mass loss is so powerful that it effectively prunes the star, preventing it from growing beyond a certain threshold. These eruptions can blow off significant fractions of a star's mass in a relatively short period, reducing the star's gravity, lowering radiation pressure, and thereby pushing the star away from instability. Studying these giant stars also illuminates how the end of a supergiant or hypergiant's life might proceed. When their size and mass reach such extremes, these stars cannot maintain the delicate equilibrium of forces, setting the stage for a supernova or hypernova explosion. This terminal event does not mark the limit only to their lives, but also to the maximum size and mass that stars achieve at any point in their existence. Interestingly, the remnants left behind, neutron stars or black holes, carry the signature of the progenitor star's mass. Black holes formed from the most massive stars hint at original masses that approached or even surpassed the stellar limits discussed. Observations from gravitational wave detectors, such as LIGO and Virgo, show black hole mergers involving objects tens to hundreds of times the Sun's mass, raising tantalizing questions about how massive stars can be and what happens to them at the end. But even these exotic phenomena fall into lines drawn by physics. There is a speculative frontier beyond normal stellar sizes where extremely massive stars might have formed under exotic conditions, perhaps at the centers of dense stellar clusters or primordial gas clouds. Here, runaway collisions or mergers of smaller stars might create supermassive stars with masses upward of thousands of suns. These objects, however, are thought to be rare and short-lived, quickly collapsing into black holes without spending much time as conventional stars. Overall, the limits to stellar size reflect an intricate interplay of physical laws and astrophysical processes, from nuclear physics deeply embedded in the stellar core to the impact of radiation, rotation, and mass loss on the star's outer atmosphere. These boundaries, while challenged and refined continuously by observations and theory, provide a consistent framework for understanding the stars we observe and the cosmic cycles they drive. The question of how large a star can grow connects to the broader quest of understanding cosmic structure and evolution. Massive stars, through their lives and deaths, enrich galaxies with heavy elements like carbon, oxygen, and iron, materials essential for planets and life as we know it. Their explosive ends generate shockwaves that can trigger the formation of new stars, propagating the stellar life cycle. Moreover, by defining the upper size limit, astronomers gain insight into galaxy evolution over cosmic time. Galaxies brimming with massive stars light up the universe, but as those stars explode or collapse, they also shape the galaxy's chemical makeup and star-forming capabilities. The limits on star sizes, therefore, are not just about individual stars. They ripple out to the grand scale of galactic development and even the emergence of habitable worlds. In practical terms, improving our understanding of the limits on star size requires continued observation across multiple wavelengths: optical, ultraviolet, infrared, and X-rays. Each spectrum reveals different layers of a star's atmosphere or the effects of its winds and eruptions. Observing massive stars in various environments, nearby and distant, young and old, metal-rich and metal-poor, helps build a more complete picture. The advent of new telescopes, such as the James Webb Space Telescope, JWST, and advanced ground-based observatories, promises to extend our reach into the universe's past and present, refining our knowledge of massive star formation and evolution. Understanding the true limits of star size is key to deciphering the earliest stages of galaxy formation and the nature of the first black holes. In sum, stars cannot grow without limit. Although some stretch themselves into truly gargantuan sizes, the physical laws encoded in gravity, radiation, fusion, and angular momentum impose boundaries essential to cosmic order. These limits define not only the lives of stars, but also their deaths and the legacies they leave throughout the universe. The stars' sizes are a carefully maintained balance between competing forces, one that keeps these luminous giants from tearing themselves apart, guiding them instead towards their eventual dazzling and often explosive ends.